Okay, 1 October 17th. Let's get right on to it. Parallel courses. You are given integer n, which indicates that there are n courses labeled from 1 to n. You're also given a 2D integer array. Relations. Where relations J is previous course and next course. That notes that a course, previous course, has to be completed before the next course. Furthermore, you're given a zero-indexed integer array time, while time I denotes how many months it takes to complete the I+1th course. Oh, courses is 1 to n. Courses is 1 to n, and relationship, this J doesn't mean anything. Previous course, I just say 1 has to be before 3, 2 has to be before 3. You must find, you may start taking a course at any time if the prerequisites are met. Any number of courses can be taken at the same time. Return the minimum number of months needed to complete all the courses. Such that it is possible to complete every course. The graph is directed acyclic graph. So this will give us the graph, right? This will give us the time. So the graph is deterministic. We already know the graph. So what we need to find out is the minimum number of time to take. So in this case, to take, so it's 3 months, right? And then plus 5 months, 8 months. Minimum number of months needed to complete all the courses. Okay. So if we topological sort it, and we start with all the ones with 0 in degrees, okay, so these are 0 in degrees, and we need to take the ones with the longest time, because the ones with the longest time, yeah, it does say that they can be taken at the same time, right? Any number of courses can be taken at the same time. So therefore, if we go topological sort, not really topological sort, just find the nodes with 0 in degrees. They have to be taken first. And we find the ones that has to take the longest. So once that longest is taken, everybody else is taken. And then we go one layer deeper, and do exactly the same. So in this case, we have these these 3 are the, actually we can try. These 3 have 0 in degrees, so they will take first. And this one has the longest, right? The longest time. So it takes 3 months. And after 3 months is over, this is the next one. So take 4 months, so 7 months. And it takes 12 months. 12 months. I think that's pretty much it, right? That's pretty much it. So we need a priority queue in which we are going to put, hold a second, priority queue. Not necessarily priority queue. Well, we're gonna put all the ones, so the months, right? It has to go to the front, the largest one. So we put that and the in degrees. Yes, put that and the in degrees in it. And as we pop this, we record the current in degree, right? It's 0, so the next one is 0. We'll do it, we just pop. So the priority queue will have to, I don't know if I want to do priority queue. Maybe not priority queue, because all we want is the longest, right? So, we collect everything, and then we go for the next one, right? we go for the next one, and if it has in degrees, it becomes 0, then we record which one. And then we collect everyone has in degree 0 at the next level. Yeah. So I just need, hold on, I think I don't need priority queue, because all we want is the max month, right? I think that's what we want, just the max month. If we have the max month, shall be fine. What are you looking for? We're looking for max month. Okay, we're gonna give this a shot. All right, so we can say in degrees. Okay, and Q. And not really. It's not necessarily a queue. It's just a. Well, you can call it a queue, right? So we call it a queue, but in fact, I think array list. We're gonna do list queue, right? And then we are going to say int minimum, no, max t, okay, and for relations. So that's the pre and next. So we're gonna say int tuple of relations. So int pre top 0, int pre and what should I call it, next top 1, right? So when we have that, now we say in degrees next plus plus, right? And then max t, max time. Oh, max time should be, no, we shouldn't do it at this point. Let's get the in degrees first. Okay, so we get all the in degrees. Oh, we also need dirt. We also need the graph. Shoot, this is later. So we need in degrees. Okay. We also need graph. Well, how are you gonna represent a graph? I want need a set. So list, right, of set integer equals graph. Array list. Yeah. Array list. No, I don't want array list. I want set integer. New hash set integer n. Sure. I don't think it's right. I want to create an array of hash set. Maybe I don't do this. Actually, that's interesting. I don't know. Integer. That's interesting. How to define that? Java define an array of set list. Yeah, I guess. Okay, that's fine. That's fine. But then we might as well just use. You cannot initiate an array of generic type unless the type argument is the unbound wildcard. All right, that's fine. We'll do array list then. So a list of this new array list. Okay. And then for int I equal to 0, I smaller than n, I plus plus. Remember, it has to -1. That's fine, I know. Graph dot add new set hash set. Okay, so that's that. Now we're gonna handle in degrees, right? And then we can say graph dot get because pre -1 dot add next. So we get a graph, we get in degrees. Now we have q. Then we say for in degrees int I equal to 0, I smaller than. Oh, let's do this. Right, now we get everybody to this one as well, -1. There we go, smaller than n, I plus plus. So now we say if in degrees I is equal to 0, q dot append add at what I, and we need a int max t and int res equal to 0. All right, and we say max t shall equal to max dot maximum max t and time I. Blah blah blah. We're done. Right. Now what? Now gonna be while is empty, q is empty. If q is not empty, we'll create a new one. We can say list integer temp new array list. Yeah, I'm still thinking if it's possible to not do it this way. If you don't want to do it this way, then now I want to do one level, right? Level, each level. Yeah, it's fine. It's fine. Then we just go through all the queues. All right. We go through all the queues. You know what? This one can be inside. Yeah, we create this. And we have to go through the queue anyway. So we go through the queue, right? So max t, yeah, don't do it here. And no, don't do it here. Of course, don't do it here. Right? Right, and then while queue is not empty, we create a temp, and then we'll go through all the queue for int node of queue. Right, and we say max t shall equal to max t and time node. Right, so go through that, and then for each one I need to find its next one, right? And we say for int child of graph.get node. Okay, so the child, and then we say in degrees child minus minus, and if I might not need to. Yeah, I don't think I need a set. I don't think so. I think a list will work. A list will work. Then in degrees child, if it's equal to 0, right? If it's equal to 0, then temp.add child. Right, so we go through all the child, get all that. And so we're done. Res plus equal to max t equal to 0. No. For int node, this one shall be done on the outside. So when this is done, we do this. All right, once it's done, say q equals temp. Assign temp into q, go back up. Right, now we try it again. Go back up, try it again until at the end. Then we'll return res. Does that make sense? Makes sense for the first one. Makes sense for everybody. Does not make sense for this one. Oh. Okay. To draw this. Nine nodes. Okay, so we have 2, 7, 2 to 6, 3 to 6, 4 to 6, 7 to 6, 2 to 1, 3 to 1, 4 to 1, 6 to 1, 7 to 1, 3 to 8, 5 to 8, there's no 5, 7 to 8, 1 to 9. 2 to 9. My goodness. 6 to 9. 7 to 9. This is impossible. Okay, this is not good. We know a lot of things go to 9, so I put 9. So I have 1, 2, 6, 7, right? 1. And we know also a lot go to 1. So 1, 2, 6, 7. And a lot will go to 6, 7. I think 2 shall be here. Right? And then we have 1, 2, 6, 7, 8. 3, 5, 7. So we have 8, 3, 5, 7. So 3, 5, 7. 3, 5, 7 to 8. And then to 1, 2, 3, 4, 7. So 4, 2, 2, 3, 4, 6, 7. 6, 7. And 7 to 6. 4 to 6. 3 to 6. God. 2 to 6. 2 to 7. I don't think I can even analyze this. Okay, hold on. We need to we have graph, we have this in degrees. So we have relations. And I think the last one is time. Okay. This is the time. All right, let's see if we can debug this. Let's take a look of how everything looked like. This is time in degrees. So 0, 1. Oh, doesn't match. These values need to reduce by 1. That is going to cause a lot of issues. This is 3. This is 1. This is 0. This is 8. This is 2. This is 5. This is 6. This is 4. This is 7. Okay, so 0, no, not 0. 1, 2, 3, and 4. Okay, 1, 2, 3, 4. We have 9, 5, 9, 5, 8, 7, 7, 8. Alright, so 0, 1, 2, 3, 4, 5, 6, 7, 8. So 0, 1, 2, 3, 4, right? 1, 2, 3, 4. So max time is 9. Oh, we don't wait for all of them to finish. I think that's what it is, right? So in my case, I say I'll take 9, and once they finish, so we have to take 9 no matter what in the first, but 1 will finish, and when 1 finish, 3 will finish. So now this cannot go. So one of them may be 6. 6 can start. So what's the deal? Some can progress faster. I think that is the reason. Yeah. Okay. So we know the current step will take 9, right? So current step will take 9. And so we need to find the one with the max cost. Okay? So 9 has the max cost. So 9 comes out first. Okay? Then we say current is 9. And then once this 9 handles, right? So our current is 9 with 1, right? Toss 9. And then this is not ready. This is not ready. This is not ready. But this is ready, right? 9. We say when 9 is done. We shall go through all the others to see 4. I mean, in this case, when this finish, anyone's ready to go, right? How should we do this? We know the max is 9, so we start from the minimum, 1. Right? Minimum is 1. So this is the maximum. So we start from minimum 1. And 1 is 5. Right? So 1 is done. We have 4 extra. We have 4 extra when 1 is done. Right? And then we check from 1, starting from 1. We check to see if who is going to be So 1 is done. We have 4 extra time that somebody else can use. Right? Somebody else can use. So I pull somebody out. Yeah, I pull 6. So 1 is done. 0, 0 is not ready. 8 is not ready. 5 is not ready. 6 is, we can start with 6. So 6 we shall push into the, and 6 is no longer taking 7. Right? 6 is no longer taking 7. 6 is the next level. So 6, instead of pushing 7, 6 shall say, when this 9 is done, 6 only has how many left? 6 only has 3 left, right? And it needs only 3 left. So this only needs 3 left, right? And then we go for this. Well, when this is done, yeah, everybody else cannot, right? There's no, but let's say this, when 3 is done, can go. When 4 is done, can do. But 6, the next round, when we do 6 has less, need to wait less time, right? Need to wait less time. So in the next round, we have something we have already done. Now there's another situation if we have to wait for so long, right? And then the next level, it might get negative, right? It might get negative. If it gets negative, then, which means this is further time that the next one can use, right? The next one can use. So it's 5. So 9 minus 5 is 4. There's extra time, but if I say minus 2, so I actually have more extra time. So if I make this change, okay, if I make this change, this is all fine, right? So we get a max t, right? And now we find if that's equal to 0, okay, so you will go for the next one, but your time is changed. Like how your time changed. So time child then shall equal to current max t minus time node, right? This is the extra amount of time, and then this shall be minus equal to, right? Minus equal to, so whatever extra amount of time I can, already start. So if I do that, shit, it didn't work. I thought it would work by making this small change. So notice 1. One is 5. Child. I have a 0, 8, 5, 6. Child is 6. 0. So temp add this. Max t. How is max t is 5? That's not right. That is not right. That is not right. This is not right. This is not right. Okay. We need a next max t. We handled this already. If this next max t shall equal to once we're done, max t equals to next max t. Does this one work? Oh, this one looks promising. Let's take a look. This one works. Okay, it works for all this. It works for all this. God, you kidding me? The first one, output 7. What? Output 7. How did you get 7? Seriously, how did you get 7? Max t. Oh, my bad. Is this? My bad. No. You're kidding me. You're killing me, man. It shouldn't be 3? What the hell? Next max t. Okay, we have these two. We have a child. And in degree. If in degree is 0, yes. Temp.add. And time max. Max t is 3. Okay. Minus. Oh, hold a second. Hold a second. If this one gets first. Wait. If this one goes first, then in degree minus is 1, so we don't do this. Now the next one comes in, and now becomes 0. Then this, I see. See the problem? You see the problem? I see the problem. I need to know also the longest time. The longest time that it takes what am I supposed to get when I reach this? Time point is this time point, right? The tick so far, right? We want to know the tick so far when you reach this. Tick so far, and then say, okay, the tick so far is 3 months. Next one, if it's 2, then it doesn't really matter, right? Tick so far. If I have multiple reaching this node, we want the maximum tick. Extra, right? Extra time. Basically, it's extra time. And I need to collect the minimum extra time. Yes, minimum extra time. So maybe the in degrees extra time. So I need an extra. Hold on. How about we do extra time? This is definitely right. We have to. The max t is not like, so we have to get, let's say, int extra time. Okay, so we have extra time. And extra time. Can we dot fill? Array dot fill? I would just say for int I equals to 0, I smaller than n, I log plus. Extra time I equal to, we want a very large, because we want a minimum, right? Minimum extra time allowed. So really large value. 1, 2, 3, 4, 5. Yeah, a large value. How do we do that? Okay. Now I can say extra time, this child, shall equal to math.minimum extra time child, and max t, right, minus time node. Extra time. Is it max or is it min? Min, but it might get to negative though. So if I have multiple nodes, nah, this should be the maximum, right? It's the maximum. Wait, hold on. It's the maximum or minimum? We have 3 comes in, right? Extra time is 0. 2 comes in, extra time is 1. So we take 0 instead of taking 1. But what if... No, max time minus this is always going to be... Always, yeah, I think it is to get minimum. Because the max time minus time node, right? So the minimum is 0, right? Minimum is 0, which means this is fine. Well, we get a minimum extra time, and once it becomes 0, so we have the minimum extra time that we can allow for the child. So that should be this one minus, right? Extra time child. The extra time that allowed the child to have. And when you do max t minus this extra time that's allowed, and this is the additional time that this one can run, and then we do the max t. Okay, let's try this one. It's even more wrong. It's even more wrong. What the hell? What the hell? Extra time math También, extra time this, and max t should be 3, right? Minus time of the current node, it should be 0, so extra time will be 0. And next one will be 1, so extra time will be 0. Oh, this is not right. This is... Hold on. Extra time. So shall just minus equal to extra time, right? Minus equal to extra time. Minus equal to extra time. So if extra time is negative, which is possible. No, not negative. It's the time child might be negative. Okay. We have this. $33. What the fuck? Oh man, this extra time is not right. Let's try. Hold on, let's copy and paste this. Why would this not be right? So for each child, for each node, right? It will lead to all the children. And we say when this one's done, all the child in degree minus 1, that's correct. Extra time is this child has based on the current. So it's max t minus the current node, current time. That's extra time that the child can execute, right? That can execute, but we don't know if it can. And it might be multiple nodes connecting to it. So we want the minimum, right? Because the max t minus the current whatever node, and eventually we'll get to the child. I don't know why this one's not right. 33. Jesus. just a little bit too complicated, so it's hard for me to trace it, right? It's hard to trace, but we do know that, hold on, let's just debug again. Okay, your current node is 1. So 1 will go through child is 6. When child is 6, extra child, extra time, the one child is 6, and in degree is 0. So we add 6. So time child, extra time child is 4. Yes. Yeah, extra times because I did 5, but it should be 9, so I have 4 extra time for 6. So 6 can execute 4, which means time child will become 3. Right? Time child becomes 3. And next max is 3. Right? Next max is 3, okay? So next child is 9. No, next child is 5. The 5 is not ready. Right? 5 is not ready. But we can collect extra time for 5. But 5 is not ready. Right? 5 not ready. But extra time 5 is also okay. Yeah, 5. And then 5 is not ready. So you're saying at the start, maybe we need to reset all the extra time. Because if at the current round, right? Yeah, the current round, you have whatever you have. In this case, right? 3 and 1, they all finish at 5. So we say, oh, but 2 and 9. So we'll make extra time and 5 becomes 0 again. Yeah, so this one becomes 0. Extra time and 5 will become 0. Then next we go. 6 will be 3, right? I don't know. Anyway, so in degrees, done. So time and then 5, 0, 1, 2, 3, 4. 5 doesn't change. 5 is still 7. Okay? But extra time 5, we have a value. So next, 0. And 0, the same thing. Next is 8. The same thing. Okay, next one is, notice 2. Okay, so 2, first child is 5. Okay, first child is 5, and 5 has extra time, 0, 1, 2, 3, 4, 5. 5 has some extra time. And extra time, now 5 shall extra time becomes 0. Yeah, 5 extra time becomes 0. But then, when 6 comes in, right? Let's say this is all done, 6 comes in. Yeah, like in this round, we didn't get any benefit for the current round. I think it's the reset. Hold on. Extra time, right? And what if we reset What if at the end, right, for a node, we go all through this node and we get the next child, right? So the next child is ready, we know what time it takes, and then we simply reset extra time. We reset extra time. Yep. I think that might be it. Hold on. Reset extra time. Try this. Ugh. Alright. Now at this point, I think it's time to give up. It's already it's already yeah, I'm gonna check. This is way too much. Oh jeez. What is the earliest time a course can be taken? How would you solve if all courses taken equal time? Yeah, well, I know topological sort, but this is extra stuff. Let's see. Topological cons. I feel it's very close. Hold on. Yes. Notes in green are the same ones. We already established that it takes 9 months to complete those courses. That's the start. The red course. The other 2 nodes. Ooh. But topological sort, these will go first. So it take 8, right? And in my view, when you take 8, this has extra 4. So this is 1. Right? This becomes 1. Now it will be 14, right? The only thing that matters for the completion time of each course is the latest prerequisites to be completed. Yes. Simplify the problem. Let's define the value of a path as the sum of values of each node on the path. Consider all paths starting from nodes without any prerequisites. The answer problem is the maximum value of such path. Hold on, so we topological sort find the root, right? And then we go through this and we're saying to take all the classes, the ones buried deep must be the ones that have the most prerequisites. So you just go through all the prerequisites. Hold on. So what are we saying? So we have this, right? So these are the first round. So so we say from this to this we have the time. From this to this we have the time. From this to this we have the time. Okay? And then once it's done, we have the time that it needs the, like, after what time this will. So this one we can get the value, like the current time. Right? The time, that's the time, it's the ticks, right? So in this we say the tick become 8, the tick become 9, the tick is 9. So this one, the tick is 9 when it's ready. And this, we say this tick is 12, this tick is 13, but it's not ready. Okay, so that's done. The next one, this will be 9 for this. So the tick is 14, so this tick become 14. So I think what it means is, so we still do in degrees, right? We do graph, relations, we do Q. We don't do this, we do ticks. Ticks, int n, right? So we say ticks I is the time is when node I is taken earliest, is the earliest time, is the earliest time when node I is taken. So with that, we don't need to do that. Rest, we don't need to do that because what we want is the largest tick. So we don't need this, nor do we need this, nor do we need this. So we go through this, and in fact, I think I can use Q in this one. Yeah, I think I can use Q. I think I can use Q. Linked list. I think I can use Q. I don't need this, nor do I need this. We simply say int node is equal to Q dot pull, right? So we pull it out, and for int child, right? So int child for the node, child minus minus, then we need to update the maximum, right? So ticks child shall equal to max math.max ticks child and time node plus not time node, ticks node plus time node. Right? Hold on. We have the tick and then plus time. Yeah, time node. Tick node. So like the time that node gets executed, right? Earliest time plus this will be the earliest time that the child will be executed. So we do that. And once this is equal to 0, then we will push into the queue, add child. And no need to do all that. So we push into the child. So in this case, we have 3. A tick is 0. These tick is 0, right? So child, so 5 gets out. This one minus minus. Tick this will equal to 0 plus 3. So it'll be 3. That'll be 4, which means tick this will become 4. Tick this is 1, so it's 4, right? So tick 5 is 4. Now, so when 5 gets out, its child is this, right? Its child is this. And then its tick is 4. Its time is 5. So this tick will be 9. So we'll do all that. None of this is needed. And it's always false. Well, I polled. Right, I poll. Oh shoot, I delete something I'm not supposed to delete. Dude, sorry. Yeah, forgot. Then we'll return the maximum. So int res equal to 0 for int t of ticks. Res equals to mass.maximum res and t. Return res. Okay, let's try this one. I thought it works. Output 3. I think I forgot to add the last one. Yeah, I think I forgot to add the last one. Okay, so hold on. So int I go to 0, I smaller than n, I plus plus. Result shall be maximum ticks I plus time I. That makes more sense. Because we want a total time. Yeah. Yeah. Let's try this. Yeah, okay. This is a solution. I'll call it hint or call it no. That's just a fail. It's a fail. Good question though. Good question. We're close. Okay. I know it is topological sort to start from the nodes with 0 in degrees. I also know that for all the nodes at the same level, same in degree level, the time it takes should go with the node that takes the max amount of time. However, what I was going for was to find out how much extra time a child node can have based on the situation of the current level. Unfortunately, this method cannot handle complex relations. Yeah. It is just too complicated, right? To figure out the exact extra time a child can have based on some previous levels. Now, the official solution offers a different view of the problem, right? We still start from nodes with 0 in degree. That's the same, right? With 0 in degree. Then we can monitor the latest, right? The latest time needed for any node of next level, right? Latest time for any next level. Monitor the latest time needed to reach, right? To reach any node of the next level. Now this determines the earliest time that the node of next level can start execution. Thus, if we keep track, right, of the earliest time that a node can start executing, right, we will be able to we'll be able to cascade this computation for the next node and the next node. In the end, we will have the earliest time needed to execute any node in the graph. Then the answer is the max value of such earliest time plus the time needed to execute the node. Yeah. So here, the earliest time that a node can be, that a child can be executed is the latest time that one of its parents, one of its ancestors, parents, one of its parents, the latest time one of the parents finishes. Close, or very close, but so close but so far away. It happens so many times, right? So close but so far away. Oh. ON. O relations. ON. What is this Q? Everyone is ON. Yeah, I think it's ON. ON plus E. Yeah, ON plus E. That's right. I can say OV plus E. Not really that hard, honestly, but DFS node is the max value for all paths starting from node. Each neighbor of node and call DFS neighbor. Take the max value of all these calls. We update DFS node using the call system. Node is wait, hold on. As a maximum value of all paths starting from node. If node is not a prerequisite, yes. If it's not a prerequisite to any courses, then we simply return the value of node. Otherwise, we iterate over each neighbor of node and call DFS neighbor. Then we take the max value of all these calls. So then what we know is the max time or the max duration it takes to start from each node going to the end, right? Start from each node going to the end. So that's the, yeah, so basically we're saying if we treat any node as the root, then what is the max time needed to finish all the class starting from this node, right? Starting from this node, what is the max time needed to finish everything? So we start from this node, right? And then what is the max time of this, and then we find out what's the max time. So max time will be, so what you're saying is this is solution number 2. Hold on, we need this. So we have solution number 2. The DFS plus DP solution. We define DFS node to return the max time needed to finish all the classes starting from node, right? Starting from node, all the classes starting from node. The non-maximum time is the minimum, right? Minimum time needed to finish all. And we go through all the nodes. We consider, right? We consider all the nodes as root to find the min time needed. Yeah, that's it, really fun. We go through all the nodes, right? We go through all the nodes and the max of all the DFS nodes is the answer. Yeah, this one's very, very straightforward and no need to do topological sort, which means we only need the graph, okay, and don't need this. We'll probably just say top 0, right? And this is top 1. Okay, and then we can do a dp. Int dp shall equal to new int n, which is, say, dp I is the minimum time needed to finish all the classes starting from I, node I. Okay, then we'll do DFS. This.dp, go to new int n, right? What's next? Def private int dfs node, right? If integer, so if dp node is not equal to null, return dp node. Okay, and then we say we probably need graph as well. Okay, then we say if graph dot get node, right, dot size dot is empty, then dp node equal to time node, return dp node. So we need time. What else? Now we have to go through and say for child of graph.get node, right? We want to know the maximum of each. The db node actually can initialize. Now we shouldn't initialize. We can actually do this, right? dp node. Hold on. Int next time. Okay. Then we say next time shall equal to max dot maximum next time and DFS child, right? So the child, the max time it needs to finish this next time, so we get the maximum time it needed to finish all those. Once we're done, we say dp node plus equal to next time and then return dp node. So that is our DFS, right? So we'll just call DFS. No. We'll say for this DFS DFS I. We'll give the max, right? And then we can say int res is 0. We can say res equal to max dot max res and DFS I, and then we return this. Is this right? Yeah. Simpler. Same thing, O and V plus E. Yeah, it's not difficult, so I'm a little bit disappointed that I didn't solve it. It's not hard at all. I should think about this DFS method, right? We try to find out the max time needed, the minimum time needed to do everything, and then we realize that you're starting from anyone. If you consider that as then you know the minimum time needed, you start from here, the minimum time needed to complete everything, right? The minimum time needed. But if you start from something else, that will be slightly different, right? The minimum time needed to complete. So for this node specifically, the minimum time needed is for this, and you go for another one, right? You go for another one, then the minimum time needed to do that. No, I think the DFS is not as straightforward. It's not as straightforward. I think the straightforward one is the top-down, is the topological sort, right? But just the topological sort, you need to realize that what we want to find out is the earliest time that each class need to start. The earliest time that they can start. This is, how should I put it? Easy problem, but not able to solve it. Anyway, that'll be it for today. I'll see you guys tomorrow. Adios.